In this video, we will learn about the two major types of autoencoders, which are sparse and denoising autoencoders. So let's get started.
Sparse and denoising autoencoders.
So one thing that we can do is that we can restrict the model's capacity based on whatever data we get on this data distribution. So we want to be able to choose a model's capacity based on the complexity of this data distribution. And that will allow us to not even have this bottleneck in the first place. So we can have a dimensionality that can be greater or equal to the dimensionality of the input. Now that means if we don't do anything about this, then the model in this case will definitely have the model capacity to just copy everything. And that wouldn't be very useful to us. So it wouldn't give us any useful representation for the downstream task. But what we want to do is that we want to instead introduce different ways to regularize this model. So we can, for instance, add a penalty. We can require the model to put as many as neurons in this code layer H to 0. So we can say you get lots of neurons that you can use, but in principle, you have to have most of them with a value of 0 as much as possible. Then again, you're restricting the capacity, but it will be restricted based on whatever the input data you get. So it's not an architectural choice so much as in the undercomplete autoencoder case, where before you have to decide how it runs, you actually give this hidden layer and instead add a penalty term in your loss function. And that will decide based on whatever input you see, how much it makes sense to actually introduce this sparsity. Next, you can change your reconstruction cost not to have this particular sparsity penalty, but you introduce a different objective. You can say that you want your autoencoder to reconstruct your inputs, but you say I'm only going to show you corrupted version of these inputs. So you will add some noise terms and you will introduce the corruption process. And then you train the model to give you the denoised variant. So you actually train it to give you the right noise-free answer. And again, you can't just do that by copying. Then you would copy the noise and you would bring down the training error. And you have to actually learn the contraction towards the manifold where the data lies. And the third way you can use, in addition to the sparsity and the denoising objective, is to use what is called as a contractive autoencoder. And the contractive autoencoder puts a penalty on the derivatives of the hidden layers activation. So you can say that you want your hidden layers activation to change very slowly as you see your data points. And that can also actually introduce very good codes actually in your hidden layer. And the idea behind that is that even if you have pixels on your camera changing very quickly because the object moves, the underlying causes that cause these values of camera pixels, they're not suddenly disappearing or something. So they will still be there. So these might move around, and in general, this causes your variation that you see in your camera, and they should actually change slowly. So then you get to this contractive autoencoder. Now I'm not going to go into too much into detail, but if you want to learn more about this contractive autoencoder, then I urge you to look at chapter 14.7 in the deep learning book for more details. Now let's look at sparse autoencoders. So what we saw before is that we can introduce this sparsity by penalizing how many neurons are there in this hidden layer at one particular point for every given input that we show the network. So what we do is that we have our reconstruction loss, that is basically this part that you see here, and then we add another penalty term here, that is omega of h. So we can just say that I want to have the sum of all the absolute values of h neurons in my hidden layer to be added to the loss. So you should actually keep the absolute value of the h neurons as small as possible in order to bring down the loss. So this is often used as a pre-processing for downstream tasks, and you can interpret this as a way of looking at the training as approximating the maximum likelihood training. And we can in principle optimize the negative log likelihood of our model, of the data under a model. And in general, we would model the joint distribution between the visible values of X and our hidden layer weights and activations H. And we can basically break this down again as a prior over the hidden layer activations. That is basically P of model H, and that's P of model H times the likelihood of our inputs under H. So that gives us P of model of X given H. So we can marginalize out our hidden codes H so that we can say that the log of the probability of data under a model is just the log of the sum over all the values of H can take on of model P of H and X under the joint distribution. So what we actually want to do when we introduce sparsity penalties is that we want to approximate this particular sum. That is the sum of these guys basically, as you see here, with a point estimate for just one highly likely value of H. So instead of using a complete prior distribution, we would just estimate a point estimate for a very likely H. So we are maximizing this probability of H and X, and we can then just convert this product into a sum. So we're taking the log of P model of H plus the probability of X given H, and now we can basically decide what we actually want to use here in order to make something like a sparse code. And one particular distribution that we can choose to give sparse values would be this so-called Laplace distribution. And the reasoning behind that is that we want a distribution that is highly peaked around 0. And if we want the neurons in the code H to have a very high probability of having the value 0, then this Laplace distribution that you see here is a very good choice. So it basically has these peaks around 0 that you see here. So the general formula of the Laplace distribution is given here. So this lambda over 2 times e to the minus lambda times absolute value of h of I, and this lambda can have basically more parameters. So you can either shift the mean, that's what you see here. Then you can either shift the mean around. So if you see here, this the mu is basically minus phi. You would then subtract that from the h that you see here, and then you can also have basically a bias parameter. Basically, the bias parameter is hidden in this lambda that you see here. So this is much more peak distribution, for instance, in comparison to a Gaussian, where we would have a much basically flatter, rounder curve like this, as you see here. So there's a lot more probability mass distributed here on the sides, and this one is much more peaked. So this way you can quantify this by looking at the so-called kurtosis, and this is the third moment of the distribution. And this is usually much bigger for Laplace than for a Gaussian distribution. So if we choose that as the prior for our hidden codes, then this is what it actually corresponds to, the so-called absolute value penalty. So if we choose this particular prior, this would give us exactly this absolute value penalty. So lambda is just a weighting factor times the sum over all I of the absolute values of hi in a hidden layer. Now this is equivalent to the negative log probability of our hidden units h under this prior. And then since we are taking this log, what we are left with is this particular part of the exponent as we see here, and just without the minus, since we have taken out the minus as we see. So we have this as lambda times the absolute value of h of I minus the log of lambda over 2. And if you compare this to the capital omega, you can see that this is the same up to a constant, and the constant doesn't really matter for the optimization. So this is one way of looking at this regularization term, of introducing a probability distribution that will encourage these sparse values. So the way that we can actually do it is that we can just introduce this omega term that corresponds to summing up all the absolute values of our hidden units, but it corresponds to introducing something like a Laplace distribution on the values of h. So we talked about the undercomplete autoencoder, and we also talked about the sparse autoencoder. Now we said the second way we can actually force our autoencoder network to learn something useful is to force it to reconstruct the corrupted input, that is corrupted by noise. And that's what this denoising autoencoder does. So what we're doing is that we're changing the loss. So rather than having g of f of x, we now introduce this new variable as x tilde, and that is basically the corrupted version of x here. So x tilde is the corrupted version of x. And so here we have our input variable x that we put through the corruption process C, that gives us the probability of our input x that we put into our encoder to give us h. And from that we try to get the reconstruction that goes into our loss function. So in the end, then we are forced to reconstruct the clean x, the x without the noise. So what we actually learn is this reconstruction distribution. So we try to estimate what the probability of x, given what we have seen, a particular value of x tilde. Then we try to estimate that from the training pairs of the clean x's and our own corrupted x's. So we implement this corruption process in the following way. So we first sample some training samples from our training data. Then we corrupt it through this process C. So we just put it through some noise. Then we use this to estimate basically the reconstruction as the decoder function. So which gives us the probability of x given h, and h is the output of our encoder f of x tilde. So we can do a gradient based minimization. So we have to just take out the negative log likelihood of our reconstruction. We then take p of x given h. So we want to minimize the negative log likelihood of observing x, given that we have seen a particular hidden code h. And we can do that in the same way that we use it for any feed-forward neural network. That's what these autoencoders basically are. So you can do that as long as your encoder is basically deterministic. So if we also have a stochastic encoder, then we need to make use of some variational inference technique, for instance. But as long as we have the deterministic encoder, then we can just use this maximum likelihood training and train to minimize this negative log likelihood of the reconstruction, given some hidden code. So what this denoising autoencoder will do by this whole process, first if we are sampling x from our p hat data, that's what this is supposed to mean. Then next we are sampling x tilde from this noise process, and then we want to estimate the likelihood of our decoder. So how likely is it to observe x, given that we have a particular value of h, and basically we want to minimize this whole expression that you see here. So the effect of this, if we train it in this way, is that we'll actually be able to perform denoising on new samples. So if you imagine the black solid line here is the data manifold. So this is where the data lives in this low dimensional subspace of all your training data. Then you can actually corrupt your data that's on this manifold, so that your X, you can corrupt it with this corruption process C, and if the effect of this corruption is not too big, then you will be able to reconstruct it back to your original manifold now. So you can actually give it some corrupted examples in later after training, and if the corruption is on the order of what the model has seen in the training process, then you will be able to actually denoise it back to your original data before it got corrupted. So we have this contraction property, as you see here. Alright, so this brings us to the end of this video. I have two repetition questions for you. So why do we need regularization in overcomplete autoencoders? And what is the difference between a sparse and a denoising autoencoder? You can pause the video now and we'll continue with the next one.